there is a very special solution. So this is the equation that I just spent all that time deriving, okay? And here is that general solution. As it turns out, there's a very special relationship that satisfies this equation, and it's called the Hermite polynomials, okay? And so here you can see how they're written. So let's just compare this. So the Hermite polynomials are given as h of nu. Technically, h nu of y is how the function's given, okay? But here is the special relationship. Look, it's the second derivative, minus 2y times the first derivative, right? Minus 2y times the first derivative. And then now in this term, it just says plus 2 nu times the function. And here we've got this written as lambda minus 1 times the function. And that's because that lambda is a big collection of all of our constants. And as we shall see later on, when the solutions become normalized, we can relate all of those constants to that quantum number. I'm not going to worry about going down that rabbit hole any further. But what I will say is the following. So once again, the Hermite solutions satisfy this polynomial, okay? They have a very special property where if we look at, so that says h prime of, h of nu prime, and that says h of nu, e to the negative y squared dy. So this is a really important integral property, okay? If nu prime is not equal to nu, this equals 0. So in other words, the Hermite polynomials are orthogonal to each other. Fantastic. So that's one requirement of wave functions anyways, okay? But if nu prime equals nu, so if we're talking about the same state, we get a numeric answer, which is awesome. That's another thing that we need out of this, okay? And also there's, I'm not showing you like a predictor of how these Hermite polynomials come up. Here you can see what they are, all right? So this general solution, doesn't quite kind of show you how these all expand. But that's okay, because I want to show you something. There's a really handy trick in Mathematica. Mathematica has all the Hermite polynomials built into it. Of course it does. And so here's how the code works. Here's how it goes. You type Hermite H bracket, okay? That little 0 there, that is in reference to the quantum number nu, okay? And so by the way, right, let's write that down. Quantum number, we see the emergence of a new quantum number, nu, the new quantum number nu. And so basically we can start thinking of these quantum numbers as these quantized integers that give us the quantized solutions to the Schrodinger equation, okay? So that quantum number nu, that is satisfying our Hermite polynomial solution here for this equation, all right? And so just to show you, Mathematica, right, has these things built in, which is really cool. So if I say 0 and y, look, it just gives me 1, and that's the Hermite polynomial for nu is equal to 0, it's just 1. But check it out, if I make nu equal to 1, then look, I get 2y. If I wanted to keep this in terms of x, I could change that to x and it becomes 2x. We're going to stick with the y because I'll remind you that y contains all of those constants that we ignored, okay? So if I go up to quantum number 2, look, there it is, 4y squared minus 2, and there it is. If I go all the way up to 6, lovely, there it is. So that's awesome that the Hermite polynomials are already built in there. Okay. So we still don't have a solution to the Schrodinger equation. We only have a general solution, and that is the Hermite polynomial. Okay.